This is lecture 9 of module 1 neural networks in this course intelligent control. In this course we will cover what is a recurrent network, unfolding in time of a recurrent network. Recurrent network, what is a recurrent network? With a feed-forward network without feedback connection, recurrent network with feedback connection. Unfolding in time, that is a recurrent network when unfolded in time can look like as a feed-forward network, and then back propagation through time. This is the learning algorithm for recurrent network. So, what is a recurrent network? Earlier we said that if there is a neuron and there is another neuron, if I connect this from this neuron to this neuron, then this connection was not allowed in feed-forward network, whereas in a recurrent network we allow not only the feedback connection, also the self feedback. So, this is called recurrent network. So, when we have two neurons in any feed-forward network, multi-layered network, radial basis function network. So, if I connect in a forward direction, the backward direction connection is not allowed, whereas in a recurrent network not only the forward and feedback connections are allowed, self feedback, this is known as self feedback. Okay. So, this kind of structure is recurrent network. So, the recurrent network include feedback connections in their architecture. What is the characteristics of a recurrent network? Representation of time, sequence is important, right. Like for example, I would like to explain this particular thing little in detail. What is meaning of sequence? Imagine we have 5 patterns 1 0 1 1 1 1 0 0 1 1 0 0 and 1 1 0. So, let us say the what is meaning of sequence is that this pattern follows this pattern, this pattern follows this pattern, this pattern follows this pattern, this pattern follows this pattern. So, this is like imagine there is a display board, and display board I want to display this pattern first, this pattern second, this pattern third, fourth, fifth, and clockwise rotate it, right. So, in that sense the sequence is important here. In this case sequence is important, all right. Another example of sequence is the time series prediction. Any kind of time series prediction, right, like the let us say rainfall in a year or in a decade or in a century. So, let us say rainfall month wise in a year, January, February, and so on up to December. So, the pattern of a rainfall in a year is a sequence. This is say in mm. So, January is some mm, February some mm, like that, December some mm, and maybe somewhere in September it is the maximum in a particular space. So, when we are dealing with patterns in which time is intrinsic, this is called temporal patterns. Okay. That is, in a year I want to see how the pattern of rainfall. So, there is a time involved in this. So, this particular notion of sequence is important, representation of time sequence is important. I can explain another way this particular concept, saying like, so for example, I have a data pattern, this is data set. So, in this data set 1, 2, 3, 4, 5, 6, and these data which are stored in this particular stack, they are in a sequence, data stored in a sequence. So, then what happens if data is stored in a sequence, then when I have to represent this data to a network, I can only represent them in a sequence. Like in multi-layer network, if I have a data set, I can always select any of this data randomly present to the network, because sequence is not important. This point I will tell in detail in a system identification example, because this is an intelligent control course. So, a relevant example in detail I will explain. So, characteristic is that representation of time where sequence is important, this is very important. And the other thing is rich temporal and spatial behaviors, okay. That is this network dynamically very rich, you know. It has stable, unstable fixed points, it exhibits limit cycles, chaotic behaviors, and it has many other rich dynamic behavior that any nonlinear system, dynamic nonlinear system exhibit, which a static network like multi-layer network or radial basis function network do not behave or do not manifest. These networks do not manifest rich dynamical characteristics. The application of recurrent networks, of course, system identification and control, associative memory, time series prediction, temporal pattern recognition, signal classification, speech recognition. These signal classification, speech recognitions, they are all temporal pattern recognition problem. Now, we will talk about architecture of a recurrent network. These two architecture are partial recurrent network. Partial means, if you look at the main body of the network is like multi-layer network, where there are feed-forward structure in a layer wise, but at the input you can see that there is a temporal sequence, like, you know, the input to the network is xt, xt minus 1. So, this one is xt minus 1, this is one delay further xt minus 2 until xt minus n. So, here this is normally known as time delay network. Imagine we are trying to model of a function like yt plus 1 is function of xt, xt minus 1 and so on. So, when this is the dynamic model, then this kind of network is selected. In many system identification example, also the another kind of network is used where you see that this is a multi-layered network structure, main body, but then to the input to the multi-layer network, in one sequence is the delayed version of xt. So, that xt, xt minus 1 up to xt minus n. Similarly, here this is a delayed. So, this is the response is yt up to yt minus m, say. So, when this kind of structure, why we say partial recurrent? Because the main body of the network, this resembles multi-layer network, the feedforward network. So, this is this kind of networks have been used in many kind of particularly in system identification and time series prediction. Another network that here these are fully recurrent network. Earlier we saw partially recurrent network. This is fully recurrent network, and in fully recurrent network you see that the input to this neuron is coming from this neuron as well as this neuron. You can easily see that this one is given here, and again this one is given here. So, the input to this neuron is coming from other two neurons. Similarly, this neuron inputs are coming from this neuron and this neuron. Okay. So, this is this neuron and this is the other neuron. Similarly, this neuron which is your this one, and this neuron which is this one. Okay. So, in that sense this is fully recurrent network. Each neuron is connected to all other neurons in the network. Normally, Hopfield network has this structure. Hopfield network has this structure. This is little mistake here. These branches are missing. So, this is another fully recurrent network. This network and this network almost same, only difference is okay, this is. So, this network the only difference is that between this network and this network is that there is a self feedback. Okay. That is the output from this network is again fed back to the same unit. So, these two architecture are called fully recurrent. So, each neuron is connected to all other neurons, and one is without self feedback, the other with feedback. So, but we can have various, not only these are very simplistic models that I am introducing to you. There are also many other complex models, we will not be discussing them. Now, once you have an architecture, obviously you would like to use them. And as you know that once we talk about neural network, means the weights have to be learned, they have to be trained. So, the learning algorithm, there are various learning algorithms, but mainly we will focus in this class, in this course. One is back propagation through time, another is real time recurrent learning. There are others also, extended Kalman filtering and many other learning algorithms that are there in the literature. We will not be taking up those things now. Let us take a discrete dynamic equation which is y t plus 1 is f of y t plus g of y t into u t, okay, where y and u are output and input respectively. All right, and f and g are arbitrary nonlinear functions, okay. And let us say that this particular dynamic that we have written here, y t plus 1 is f y t plus g y t u t, this represent some system, some nonlinear system. Now, I want to model using a feed-forward network as well as the recurrent network, the dynamics of this equation. Okay, let us say this equation. And if I want to use a feed-forward network, what I will do is, in feed-forward network, this is called feed-forward network. So, in feed-forward network, my input will be y t as well as u t, and output is y t plus 1, whereas this is actually predicted output of the network, and y t is actually, this is the input to the network, but obtained, this is obtained from actual system. So, this particular dynamics that we are looking at, y t plus 1 is f y t g y t u t. If I really want to capture this dynamic using a recurrent feed-forward network, what I do is that my inputs are y t as well as u t, and output is y t plus 1, this is the predicted one, whereas this y t is taken from the actual system. So, I observe the state of the system at t y t, give a input corresponding a time u t input u at t, then what is my output y t plus 1 is predicted by feed-forward network. But a recurrent network in the contrary only takes the input u t, only takes the input u t, and the output is y t plus 1. Okay. That is, it is possible because a recurrent network allows feedback connection from output to input, the internal states. So, this is much like recurrent network is much like this is much like a dynamic system, whereas a feed-forward network is a static system. This is very important to understand. A feed-forward network is a static system because and while training a feed-forward network, we really do not worry, we really do not care the order of the pattern. Given a pattern, that is input output data set, I can select any pattern, give the input of that pattern to the network, forward pass that input, find what is the output, compare with the desired one, back propagate the error, update the weight. That is the feed-forward network. Whereas a recurrent network, the sequence of data to be presented to the network must be preserved. That is like now how I will present a network data to this recurrent network, U0 Y1, U1 Y2, so the sequence has to be like this here. So U0 Y1 first, then U1 Y2 second, and so on. But I cannot arbitrarily select any of these sequences and present to the recurrent network. No. So this is called, there is a representation of time in a recurrent network. Sequence is important, whereas time do not play any relationship in feed-forward network. It is a static map. The normal training algorithm that are used for recurrent network is backpropagation through time and real time recurrent learning. So these two are very popular algorithms available in the literature, but there are also other like extended Kalman filtering. But in this course we will only learn, or I will only take up these two learning algorithm, backpropagation through time, which is a offline, and real time recurrent learning, which is a online learning algorithm. So today this lecture will focus backpropagation through time. In backpropagation through time, we unfold a recurrent network in time to reach a feed-forward network architecture. So what is that unfolding? So the unfolding is, let us take a simple recurrent network which consists of only single neuron. Input is xt, the input to the neuron, the weight is w, and there is a feedback from output to the self feedback, and the weight is g. So this is a very simple network because it has consists of only one neuron. The first part is that before we talk about unfolding this network in time, when this is a feedback structure, the objective is how to convert this feedback structure to feed forward structure. So this we want to do. I want to convert this feedback structure to a feed forward structure. So how do I do it? It's very easy to do. Before we can do that, we must write down the forward response of the network. What is the meaning of forward response? Given xt, what is yt plus 1? Okay? So let us say this neuron has a sigmoidal activation function. Okay? That is, the yt plus 1 is w xt plus g yt. You can easily see that this is a feedback. So we assume that this when I put I don't put any anything on this connection, it means that there is a delay of 1 unit. Okay? So the y at the t plus 1 sampling instant is a function of w xt, the summation of all the inputs, the w into xt plus g into yt. Okay. So this is the total summation and the summed input at the input of this neuron, and then sigmoidally activated, where fz is as usual the sigmoidal activation is e to the power minus z. All right. So this is our simplest network, and to this simplest network, how do you unfold this network? So let us see this forward response that we wrote which is y t plus 1 is f of w x t plus g y t. This is the forward response of the simplest network that we took. So, if I write recursively, what I do? I write y 1 is f of w x 0 plus g y 0. Similarly, y 2 is f of w x 1 plus g y 1. Just look at this equation. I simply put t equal to 0, then I get the first equation. T equal to 1, I get the second equation. T equal to 2, then I will get the third equation. And so on. So, we can go on like this. So, how do we construct a feed forward network looking at these equations? So, what I will do in my network, I create a node. In every node, I compute what is y 1 as a function of x naught y naught and y 2 as a function of x 1 y 1 and y 3 as a function of x 2 and y 2. So, this is what is here. This is what we are doing. So, y 1 here you see that y 1 is w x naught plus g y naught. Similarly, y 2 is w x 1 plus g y 1 and sigmoidal activated. This neuron is sigmoidal activated. So, thus if you look at here, our recursive equation is f of this summation, f of this summation. Okay. So, that means you should not forget what is meaning of f. F is always a sigmoidal activated function. So, that is what we are doing here. Okay. So, y 1 is f of w x naught plus g y naught, y 2 is f of w x 1 g y 1 and so on. So, this is called rolling the network in time. Now, if you look at this network which I discussed now, if rolled over t equal to 5, so then for t equal to 1 this is the first expansion, t equal to 2 this is the second expansion. So, first expansion y 1 in terms of y naught x naught, second expansion y 2 in terms of x 1 y 1, third y 3 in terms of x 2 y 2, similarly 4 y 4 in terms of x 3 y 3 and 5 y 5 in terms of x 4 y 4. So, this is how the network is unfolding over time, and we can go ahead depending on the situation or demand. And now, once we unfold, now this is a feed forward network. If you look at this, this is a feed forward network. And this feed forward network is actually MLN, multi-layer network, with how many layers? I can say this is one layer, this is the first layer of weight, this is the second layer of weight, this is the third layer of weight, fourth layer and fifth layer. Alright. So, MLN with 5 layers of weights. Okay. So, given this structure, once I convert the recurrent network into a feed-forward network, the objective would be now to apply, because this is now a feed-forward network. So, I apply the back propagation through time, back propagation, standard back propagation, generalized delta rule to update the weights. So, how do I do it? How do I do it? Now, I have already the dynamic equation here, y t plus 1 is f w x t plus g y t. So, This is the dynamic equation. So, what I do is that given y naught and the sequence of x naught, x1, these are external input, x naught, x1, x2, x3, x4, these are all external input. So, given this external input, an initial condition which is y naught, let us compute what is y1, y2, y3, y4 and y5. So, this is the first step. First step is given the sequence x naught, x1 and so on x4 and initial condition, this is initial condition, and these are external input, compute y1, y2 and y5. So, this is how we generate the data. Once we generate the data, so what I can do is that I now forward propagate my signal. So, initial condition is y naught. Initially this w and g, they are all randomly, they are same values, but random values. Whatever w, these initially these w's are all same, but all random value, some random values. Similarly g's, they are all random. And then what I do, I take the initial condition y naught corresponding and x naught is the input, and compute what is y1, and take x1, compute y2, take x2, compute y3, take x3, compute y4, take x4, compute y5. So, once given x naught, x1, x2, x3, x4, so and given the initial values of w and g, and these w g values are all same in the initial network, and always they are actually same, because w and g for all layers are same at any given instant, because this they are not different. So, given y naught and this sequence, we can compute y1, y2, y3, y4, y5. From this model we get actual y5, y4, y3, y2 and y1. So, obviously we can compute at every target, in this target E1, in this target E2, this target E3, this target E4 and this target E5. So, what is E5? Now, the response of the network is subtracted from the actual response of the network, which is y5. So, similarly, so that is this E5 is yd5 minus y5, E4 is yd4 minus y4, like that, y desired 4. Similarly, y desired 3 minus y3 is E3, like that. So, we compute these errors at every target. Now, apply the back propagation through time. How do I do it? Let me explain again in this manner. Let us take a very simple thing, that is only 2 layer, okay. So, this is my x naught, y naught, this is y1, this is y2, x1. Obviously, this w, this is w, this is g and this is g. So, what is y2? y2 is f of w x1 plus g y1. So, how do I update this w and this d? So, this is my second layer. So, I will write w2 delta, the change in delta w2 using the gradient descent, back propagation algorithm. how do I write this? This delta W2 is eta delta, this is the output layer, so I put delta 2, the error back propagated from the second layer, output layer delta 2, and input is x1, input is x1. This is the standard generalized rule, standard delta rule. Standard delta rule. Okay. Similarly, delta G in the second layer. This I say second layer. This is second layer. This is the first layer. So, in the second layer, delta G due to the error from here is, and what is eta delta 2, and input is y1. And what is delta 2? Delta 2 is obviously the error here, which is E2 into y2 into 1 minus y2. What is y2 1 minus y2? We assume that f dash, which is df by dt, is y2 1 minus y2 when fz is sigmoidal activation function. This point we have earlier said. If fz is 1 upon 1 plus e to the power minus z, then f dash is z into 1 minus z. So, that is what we are writing. So, E2, and what is E2? E2 is y2 desired minus y2. So, given this is the first layer. Similarly, second layer will be again delta W in the first layer. So, we can again do this for the first layer now. Delta W 1 is eta delta 1 x naught, and delta G 1 is eta delta 1 y naught. Okay, because this is a standard delta rule. And what is delta 1? Your delta 1 is obviously, the not only error back propagated from here, there is also error here, and that error is E1 here, the error, and back propagated error is delta 2 back propagated through G, back propagated through G, that is the delta error back propagated, and this is your y1 into 1 minus y1. So, this represents delta 1. So, like that, using simple delta rule, we can compute, given the data sequence, we can compute what is delta W1, delta G1, delta W2, delta G2, and finally are these weight the change in weight in every layer, and sum that, and finally W is updated as W is new is W old plus sigma delta W I in every layer, because now weight, same weight has been updated in every layer, but the weight is same weight. So, all those updates that according to back propagation, that infinitesimal change in weight that we get, we add over all the layers, add them, and then add to the old weight, and that becomes the new weight. So, that is the objective here. So, So, for the network with t equal to 5, I just showed you t equal to 2. So, t equal to 5, compute the response of this sequence y1 to y5 given the sequence x0 to x4 and y0. Okay. So, we are talking about the network that we have already talked here. So, this is my total feed forward network constructed from the recurrent network by rolling over time, and for this we are showing the error. So, computed error E5 is YD5 minus Y5, delta Y5 is eta delta 5 X4, delta G5 is eta delta 5 Y4. So, we can easily see here what we are trying to do. So, E5 is YD5 minus Y5. So, this delta W, the change in this weight is obviously eta delta 5 X4. Change in this weight G is eta delta 5 into input is Y4. So, that is what we are writing here. That is what we are writing here. But delta 5 is, this is the differentiation of the activation function or derivative of the activation function and the error at the output. But when I come to the layer 4, my error at the layer 4 is E4 already is there, and the back propagated error is delta 5 into G. So, which we will talk about now here. So, the error here is E4 plus back propagated error from this layer, which is delta 5 into this weight G. So, like that we have to compute. Okay. So, this is for fourth layer, this is for third layer, and finally, this is the first layer. This is the second layer. So, this is the way we apply generalized delta rule to this feed forward network that has been constructed from the recurrent network by rolling the recurrent network over time. And finally, after finding delta W over all the layers, delta G over the all layers, what we compute? W new equal to W old, and we add over all layers delta W. Similarly, G new is G old plus whatever delta G I over all layers, we add them, and because there are 5 layers of weights, we add and then we find G new. Okay. So, we talked about a simple network. Now, let us go to a little complicated network, and is that simple network is complicated network is very difficult to roll over time? No, it is not. Once we understand the principle, rolling over time is not very difficult. Now, for example, you see here, this is a fully connected network. We have 3 neurons and 2 external input x1 and x2 and 1 output is y. And we can let us say the output of this neuron is, this is x3, this is x4, this is x5. So, y is x5. If I look at the forward response, the normal convention, if you look at, so if I look at the weight connections, the weight that are being connected here, if you look at here, this weight from the input 1, see, you see the connection x1, x2, x3, x4 and x5. So, weights are, the convention wise, the weights are, this is the node to which the connection is coming. So, and from 1. So, obviously, the weight that has been named is W31. W31 means the weight that connects the node 3 from node 1. Similarly, W33, by just looking at this weight you can say this is a self feedback weight, that is this weight connects node 3 to itself. Similarly, W35 you can look at this weight is coming from the node 5 and connecting to 3. Okay. Similarly, W45 if you look at this one, this is coming from 5 and connecting 4. Similarly, W55 is a self feedback weight. So, this is the convention of designating the weights, okay, and this is a fully connected network. So, what is the forward response? Forward response is the what are the output of each network, each neuron for given x1 and x2 and the present state x3t, y5t and x4t. Okay. So, x3t plus 1 is the response of the node 3 at the next time instant is a function, sigmoidal activation function f of the summation of W3I. This is actually a small w, W3I xit. Similarly, x4t plus 1 is again this is small w, W4I xit, and x5ty1 is W5I xit, because each node is connected to all other every node. So, all the 5 nodes, 2 input node and 3 the neurons. So, total 5 nodes. So, you can easily see that x3 t plus 1 is okay function of S3 t plus 1. And what is S3 t plus 1? S3 t plus 1 is summation, that is W31 x1 plus W32 x2 plus W33 x3 and so on W35 x5. So, this particular item that we are inserting here, which is known as W3I xit, okay, this has to be t. Time has to be there. We cannot do away with time in recurrent network like we have done in the feedforward network. So, the same network, once I know this forward response, so I can easily write down here, I can unfold this same network in time here. So, obviously, this is my x3 0, this is x3 1. So, x3 1, x3 at time 1 is a function of x1 and this is W31, and x2 this has to be W32, x3 W. So, the best way to look at it is like this. So, I have this 2 input node and this is the initial state. So, this is x1 0, x2 0 and these are all initial states. So, based on this initial state, the new state x3 1, x4 1, x5 1. So, how do I compute x3 1? x1 0, W31 is the weight connecting x1 0 from x2 0, this is W21, x3 0 W31, x4 0 W41, x5 0 W51. So, the forward response x3 1 is a function of x31 is a function of summation w3 I x0. So, based on that we found out the connection between x31 and these initial states before in the previous instant. Similarly, x41, x51, and that way we can roll this network over time. Okay. So, let us take one example today to illustrate that what we have learnt. Let us take a simple linear network, a linear dynamics. Yt plus 1 is minus 0.5 yt minus yt minus 1 plus 0.5 ut, a simple discrete dynamic equation. It is a linear dynamic equation, discrete dynamic. So, this particular equation we can represent in terms of this, that yt plus 1 is y1 yt, w1 yt, w2 yt minus 1 and plus w3 ut, where w1, w2 and w3 are unknown weights, we do not know, and this is the recurrent network. To represent that, we give xt, output is yt plus 1, and you see that there are two a feedback connection here, self feedback with one delay, and this is 2 delay. All right. So, obviously, if I expand this particular, if I write the forward response of this network, then this is the forward response. The forward response is yt plus 1 is xt into, this is w3, xt into w3, this quantity, actually this is we say xt, but in this case it is ut, xt is ut, and so xt into w3 or ut into w3 plus w1 into yt, 1 delay, plus w2 into yt minus 1, 2 delay. So, this is my recurrent network, and the activation function here f is linear, f is linear. Okay. So, f is linear. So, if I take this network, so similarly I can, from the forward response I can write what is y2, y2 is w1 y1, w2 y0, w3 u1, y3 is w1 y2 plus w2 y1 and w3 u2 and so on. So, this is the unfolding, corresponding unfolding in time, and we apply this back propagation through time using generalized delta rule. We generated 100 data points, okay, where input ut was selected randomly between 0 to 1, and given the dynamic equation that we represented, we gave for data generation. So, we used this particular equation for data generation, So, if you look at this data, the circles represent the output and the cross is ut and circle is yt. Okay. So, this is the input data generated, and then with back propagation through time we trained it, okay, and when it trained, let us see how the training took place. The RMS error over number of epoch, so was, you can see that how the RMS error reduced, okay, we were 3000 almost epoch, and and the weights, this is our W3, this is our W1 and this is our W2. So, W3 has reached 0.5, W1 has reached minus 0.5 and W2 is minus 1. So, if I go back and look at the equation that was given to us, you can see this was my W3 which is 0.5, W2 also I got minus 1 and W1 is minus 0.5. And the error surface is the plot of cost function E versus the weight vector W. So, you can see that how finally we reach the global minimum, because this is a linear dynamics. So, we can easily reach the global minimum, that is not a problem. So, to conclude, what we saw that in this lecture we learnt about architecture of a recurrent network, unfolding a recurrent network in time to make it a feed-forward network, training of a recurrent network using BPTT algorithm, and we showed an example of a system identification of a linear discrete dynamic. Using BPTT, we showed that the actual parameters are learnt. Thank you very much.